Let's take a look at the energy in a simple harmonic oscillator. The simple harmonic oscillator is an oscillator that has a single frequency. It's not a combination of multiple frequencies. And we're going to look at this without friction. So the first thing we need to calculate is the potential energy. And from Physics 215, we know that it's the negative integral of the force times my differential distance. And I can put in Hooke's law. The negative in Hooke's law is going to cancel the negative in the potential energy formula. And I'm just going to have the integral k of the spring x dx. And when I integrate this integral, I'm going to get 1/2 k of the spring x squared. Now I can calculate the total energy, and the energy is going to be equal to the kinetic plus the potential. And this is going to be a constant because we have no friction. This is without friction. So nothing's being dissipated. The energy, once it's in the system, it's going to stay in the system. And so this does not depend on time. So our energy is going to equal the kinetic, which is from 215, we know that's 1/2 mass times velocity squared, plus, and we just calculated the potential, and we can factor 1/2 out, and I have the mass times the velocity function, plus k of the spring times the x function. And that's going to be squared. Well, I can already see that I'm going to have a sine squared plus a cosine squared, and I need to figure out if I can get the amplitudes so that I can factor out and so that I can get the sine squared plus cosine squared. So that's what I aim to do. Don't want to forget the 1/2. I have m omega squared a squared sine squared omega t plus phi plus k of the spring a squared cosine omega t plus phi. That should be cosine squared. And now I can take and put in for omega squared. And I'm almost there. The m's are going to cancel out. I'm going to have a k of the spring times a squared in the first term and a k of the spring times a squared in the second term, so I can pull that out. And I'm going to have sine squared plus cosine squared left, and that's just going to be equal to 1. Now I can play around with this energy, and it's interesting, this energy is a constant. There's nothing in here that was dependent upon t. K of the spring is a constant, the amplitude's a constant. So we can play around with this a little bit more and come up with some different formulas. Well, one of the formulas that we can do is substitute in for K of the spring, and that's going to be 1/2 mass times omega squared amplitude squared, and this is also going to be equal to 1/2 mass times V max squared. And this is just when it's all kinetic energy. Now, let's take and bring this up to the top. And I'm going to make that equal to this. Now remember that this velocity is a function of time and the x is also a function of time, but they occur at the same time, so that helps us to understand that even though we're looking at same times, we can still just look at this as velocity and distance. The 1/2s are all going to go away, and that's going to leave me with, oh, I'm sorry, I forgot the squared here. So I'm going to have mass times V max squared is equal to mass times velocity squared plus Ks times x squared. Now I want to try to solve for V, so I'm going to have mass velocity squared equal to mass times V max squared minus K of the spring times x squared. And I can divide through by m. And V max squared is just omega squared a squared. Ks over m is just omega squared times x squared. And I can bring the omega squared out, and I can take the square root of everything. So V is going to equal plus or minus omega times the square root of a squared minus x squared. So there's some interesting things about this formula. One, it's a formula of velocity and x. A is a constant, omega is a constant, and basically it says that I can tell you the velocity based on where the mass is on either side of the equilibrium. I don't need to know the time value, I just need to know the distance, and I can tell you the velocity based on the spring constants. It's also interesting that you have the plus and minus, and that just means that we don't know which direction it's going. So let's say we have our mass here connected to a spring. Here's our equilibrium, and here's some value x. And it means that I don't know whether the mass is going from left to right or right to left, and it doesn't matter because the velocity is going to be this value. Doesn't matter which way it's going. And that's what this formula tells you. Now, one of the homework problems is going to be taking this formula for the energy and getting it back into the form x function of t equal to a cosine omega t plus phi. And we'll discuss how that actually works.